Alright, so this is going to be a quick intro to graphing that you're going to use to graph your data from the from experiment 2, which is the density and error experiment. So when you went through the experiment, you collected your data. You were able to measure for the different cylinders, for instance. So let's say you chose the group of cylinders that were sample A, and you had to choose 5 of them, and you were able to record their masses over here using the balance. And then based on the displacement, you were able to measure the volume of each of those cylinders. So what you're going to be doing is plotting this data on a graph, and specifically we're going to plot the mass of each cylinder versus its volume. So I'm going to upload to Canvas some graph paper, but you can by all means use your own graph paper. The key thing here though is I want you to do this, do the graphing by hand. So let me show you really quick how you would want to do this. So the first thing is you want to make sure that you have a title for your graph. And what you're doing, what you're plotting is the mass versus the volume for different cylinders. Right, so you can choose that as your title, or you can make up your own, but it should be a descriptive title that describes what it is that your graph is going to contain. Now the next thing that you need to do is, once you have your graph paper set, is you want to make sure that you orient your graph properly. So we're plotting mass versus volume, so that means mass is going to go on the y-axis, and then volume is going to go on the x-axis, right? So one of the first modules that you did on Mastering Chemistry was interpreting graphs. We're going to use some of that information here. When you plot your graph, you want to make sure that you use a ruler to make sure that your lines are all straight. I'm just going to do this freehand, just in the interest of time. So on the y-axis here, you have your mass, and you want to label your axis, so the mass of the cylinder, and then the unit as well. So this is in grams. And then on the x-axis, you have your volume, of the cylinder, and then this is in milliliters or cubic centimeters, which is the same thing, right? 1 mil is the same thing as 1 cubic centimeter. So on your graph, you're going to plot all of the data points from both of the cylinders that you measured. So you want to make sure that when you plot your graph, that you scale it such that all of your data points are going to be on that graph, and you don't want all of your data points to be clumped together in one location, in one small part of the graph itself. So you want them to be spread out as much as possible. So you need to scale your graph properly. So we're going to plot each of these data points. So for example, for cylinder 1, all right, we're going to have a mass and a volume associated with it, and we're going to plot that on our graph. All right, so let's say here now cylinder 1 had a particular mass associated with it and a volume. We're going to find those masses and volumes on the graph itself. So there is our origin. We have to label our axes with the different numbers. So let's say I'm just going to choose here, in the interest of time. This is 1 gram, that's 2 grams, that's 3, this is 4, this is 5, etc. So you will have to adjust your scale to make sure that you account for all of the masses and volumes that you have. On the x-axis, I'm going to label that with my volume, and let's say I choose this here to be 1 milliliter, so every 4 here is a mil. 2, 3, 4, that's 3 milliliters. This is 4, 1, 2, 3, and this is 5, etc. Right? So your scale may be like this, or it may be different. That depends on the data that you collected. So let's say your first cylinder had a mass of 5 grams. So we're going to find that here on the x-axis. And let's say that it had a volume, when you measured it by displacement, it had a volume of 3 milliliters. So we're going to find each of those. There's our 5 grams for the mass, followed across. There's our 3 milliliters. So we're going to find where those two intersect, right there. Put a circle around it, and that's your first data point. So you're going to be doing that for all of the cylinders that you recorded for the metal that you chose. So let's say I have some other data points that happen to be like this. All right, so you have 1, 2, 3, 4, 5 of those data points. All right, and those are the data points for my metal. So the next thing you're going to do is draw your line of best fit that goes through as many of those points as possible, but it also has to go through the origin down here at the bottom. So you want to use a ruler when you do this. The line that you draw of best fit must go through the origin, and you want to make sure that it goes through as many of those data points as possible. Now I'm doing mine freehand. You want to use a ruler to draw your line of best fit. All right, and then this here is for your metal cylinder. So I'm going to put a little legend somewhere. This data point here is for my metal cylinder. So when I plot my other set of data points on here, I can denote it in a different way to distinguish one set of data from the other one. So for my line of best fit here now, what I'm going to have to do is to come up with my equation for this particular line. And the equation for the line, for a straight line, is y is equal to mx plus b. The y here just means the y value. The x here is the x value. M represents the slope. And then b is something known as the y-intercept, which is where your graph or the line here intercepts the y-axis, and this is going to be equal to 0. All right, so if we simplify this, what this ends up being is y is equal to mx, because b, or y-intercept, is 0. So if you rearrange this equation now, we have our slope m is equal to y over x. So we can actually calculate the slope of our graph using the equation of this straight line. So you can, once you have your line of best fit, you can choose any 2 points on this line to generate the slope or the gradient. So I'm going to choose 2 points that are far apart from each other. I'm going to choose a point down here, and I'm going to choose a point up here. The points that you choose don't have to be any of the data points. They just need to be along that line. And I'm going to calculate the slope, which is simply the difference, or how much the y value changed compared to the x value. So this is the y difference, and that difference here is, let's say this is 5, this would be 6, and then this would be 7. All right, so the difference in the y would be 7 minus where we started with, which is 1. And then the difference, in the x would be this difference over here. All right, and this is equal to where we ended up with. So this would be 4.25 minus 0.5. All right, so we take away 1/2 from that, we end up with 3.75. So then the slope would be equal to 7 minus 1, the difference in the y, divided by 4.25 minus 0.5, the difference in the x value, which ends up being 7 minus 1 is 6, divided by 3.75. Right, so that's your slope. You can evaluate that, and that ends up being 1.6. So this here that you just calculated is the slope, and the slope that you calculate is equal to the density of your material. So this would be 1.6 grams per mil, or 1.6 grams per cubic centimeter. Right, so based on what we calculate, we can then compare it to the table in your lab handout. In order to calculate your percent error. All right, so if I take a look at some of the options that were given in my in the table provided. So here, for example, right, we can see that out of the options here, maybe the PVC is the closest to 1.6. So we can then compare your experimental value, which is 1.6, to the actual. Which is from the table, and the actual value would be 1.470. All right, so I'm just going to change my notation here a little bit. I'm going to say this was not a metal that we actually used. It was a plastic cylinder. So I've calculated, I've plotted all my data on the graph. I've generated my line of best fit. I've calculated the slope, and the slope of that graph is equal to the density of that particular sample. And then I can then rewrite the equation for my graph now. As y is equal to mx. And I can just substitute the value for m, the slope, which is 1.6 times x. All right, so the last thing I can do, like I mentioned, is to calculate my percent error. All right, and the percent error is an indication of your accuracy in your experiment, and the percent error is equal to what you get, the experimental value, minus the actual value that you get from looking it up, or in this case it's provided in your lab handout, divided by what that actual value is, and it's a percentage, so we're going to multiply it by 100. So in this case, our experimental is what we actually found. It was 1.6, And then we look up what the actual value was. It was 1.470. We're going to divide it by 1.470. We're going to times that by 100, and then whatever you get here will be your percent error. All right, so again, the experimental value, this here is what you get. From your graph, and then the actual value, which are these two values here, are the true values that you get from looking up. Look up in the table provided. Okay, so you can do that for your first set of data points for one of your materials that you used, and then on the same graph you're also going to plot now. On the exact same graph, you're going to plot the data for the second set of cylinders that you measured the mass and volumes for, and you can plot it here. You can maybe do it in a different color, or you can do a different notation for the data point. So for example, I'm going to do this in blue, and I'm going to write it as an X or a cross with a circle around it. All right, so maybe this could be my set of data points, and then again I'm going to get my line of best fit that goes through as many of those points as possible. And in my legend here, I'm going to say this would be my metal cylinder data point, and I'm going to go through the same process, get my line of best fit, choose 2 points that are on the line, calculate the slope, and then that slope is equal to the density of your material. You can look it up, compare it to the tabulated values to see what it's closest to, and then you can calculate the percent error in a similar manner. All right, so that's a short tutorial on how you want to generate your graph from this experiment.